Welcome to the Explainer. Ever stop and think about the air you're breathing right this second? Well, today we're going to do just that. We're taking a trip back in time, all the way back, 4.6 billion years, to uncover the incredible story of our atmosphere. Now, this is your go-to revision guide for section 4.9.1 of the AQA GCSE Chemistry spec, so let's get right into it. Okay, so this is the air we know and love today. For the last 200 million years or so, it's been this pretty stable mix. You've got about 80% nitrogen, roughly 20% oxygen, and then just tiny little bits of other stuff like carbon dioxide, argon, and water vapor. This exact recipe, this balance, is what makes all the life we see around us possible.
So, was it always this way? The short answer? Absolutely not. Not even close. Honestly, the atmosphere on early Earth would have been completely alien to us. To get how we got from there to here, we have to rewind the clock all the way back to the very beginning.
So, how did our story begin? Well, it all starts in the first billion years of Earth's life, a period of just chaos, intense heat, and non-stop geological action.
Trying to see this far back is, as you can imagine, really difficult. The evidence is pretty thin on the ground. But we have a major scientific theory, and it paints a picture of a planet that was, well, truly hostile. I mean, just look at the difference here. The scale of this change is just massive. Earth's first atmosphere was probably almost all carbon dioxide, with practically zero oxygen. You want to know what that's like? Just look at Mars or Venus today. The journey from that toxic environment to the air we breathe now is the whole story we're unpacking. So, where did all that gas even come from? One word: volcanoes. For the first billion years, Earth was basically a world of volcanoes, constantly erupting and just spewing out colossal amounts of gas. We're talking carbon dioxide, tons of water vapor, and a good dose of nitrogen, too. And here comes the first big plot twist. As the planet finally started to cool down, all that water vapor in the air condensed and rained down, forming the very first oceans. This was a total game changer, you see, because carbon dioxide can dissolve in water. So it started getting pulled out of the air and into the sea, where it eventually formed carbonate minerals that sank to the ocean floor, locking that CO2 away in sediments. The oceans got the ball rolling, but the next chapter, well, it's even more incredible. This is the part of the story where life itself arrives on the scene and starts to completely re-engineer the entire planet. Now, it's so important to get your head around the huge timescales we're talking about. These changes weren't happening overnight. From those volcanic beginnings, to the oceans forming, to the first algae, and finally to the stable air we have now, this all played out over billions of years. Right, so about 2.7 billion years ago, these simple little organisms, like algae, show up in the oceans. And they had this revolutionary new trick up their sleeve called photosynthesis. They started using sunlight to gobble up all that carbon dioxide still in the atmosphere, and as a waste product, they released oxygen. And here's the wild part. For the life that already existed, this new oxygen stuff was basically poison. But for new life, it was a huge opportunity. As plants evolved and spread across the globe, oxygen levels slowly crept up until they were high enough for complex animals that breathe, to evolve. So, oxygen levels are on the rise. But hang on a minute. For that to happen, all that carbon dioxide had to go somewhere, right? So how exactly did the planet lock away so much carbon? Okay, listen up, because for your GCSE exam, this is a big one. You really need to know the two key ways carbon dioxide levels plummeted. First, like we just said, was photosynthesis. Algae and plants were sucking it out of the air to build their bodies. And second, when those organisms died, the carbon inside them got trapped. So this trapped carbon became two really important things. First, you get sedimentary rocks, like limestone, which are made from the compressed shells and skeletons of zillions of tiny marine creatures. And second, you get fossil fuels. That's right, coal, oil, and natural gas are literally the squashed remains of ancient life, locking away atmospheric carbon deep underground for millions and millions of years. Phew, okay. Let's pull all that together. What we're about to look at is the summary of this epic multi-billion-year journey, and it's pretty much exactly what you need to have locked in for your exam. This table right here is your perfect revision tool. Look at the journey of these three main gases. Carbon dioxide starts off as the main event, over 90%, and ends up at less than 1%. Why? Oceans and life.
oxygen starts at basically 0 and shoots up to 20%. Why? Photosynthesis. But what about nitrogen? Well, it was pumped out by volcanoes at the start, but because it's super unreactive, it didn't really go anywhere. It just hung around and built up and up over billions of years until it became the main gas in our atmosphere.
And that brings us right back to where we started. This stable, life-giving balance of gases, the result of 4.4 billion years of geology and biology all working together, has been the foundation for life as we know it for the last 200 million years.
But here's the final thought to leave you with. That long, stable period, it's now being challenged. All that carbon that was locked away for hundreds of millions of years in fossil fuels, we're putting it back into the atmosphere in just a couple of centuries. Understanding our atmosphere's deep past is really the only way we can understand the changes that are happening right now and what might happen next. And that, of course, is a topic for the next part of your syllabus.